Good day everyone, I am Manzanal, a third-year geological engineering student of Batangas State University. Today, I will be presenting a study that addresses a critical challenge in rice agriculture, monitoring soil salinity effectively and affordably, entitled An Application of Soil Electrical Conductivity Measurement by Wenner Method in Paddy Field. To begin with, rice is a staple food for over 3 billion people worldwide, and the majority of this rice is grown and consumed in Asia. One of the most important production areas is the Vietnamese Mekong Delta, which plays a vital role in Vietnam's food security and rice exports. However, the region is increasingly under threat from climate change, particularly saltwater intrusion, which affects not only rice yields but also the livelihood of millions of smallholder farmers. To address this, one of the most effective ways to assess soil conditions is by measuring soil electrical conductivity, or EC. EC provides insights into soil salinity, texture, moisture content, and even crop yield potential. Using EC maps, farmers and researchers can apply precision agriculture techniques like adjusting fertilizer or irrigation based on actual field variability. But there is a gap in the current research. Most EC studies have focused on crops like corn and wet and dry climates. Very few have explored EC in flooded rice fields, particularly in regions like the Mekong Delta. And unfortunately, the tools typically used, like imported EC meters, are often too expensive or impractical for small farms. This study aims to fill that gap. It tested a low-cost, direct-based Wenner method to measure soil EC at 3 different electrode spacings, 5, 10, and 30 centimeters. Then the researchers compared those results with the commercial HANA HI98331 EC device to evaluate accuracy. Finally, the researchers created EC maps using Surfer software and kriging interpolation to visualize salinity patterns in the field, an approach that can help guide smart, targeted interventions. The study was conducted in Toi Lai, located about 20 km west of Can Tho City, in the Mekong Delta, Vietnam. The site includes 2 zones of alluvial soil used for wet rice cultivation. Zone A, 4,000 meters squared, and Zone V, 14,000 meters squared. The area typically supports 3 rice crops per year, but is vulnerable to flooding from June to November due to seasonal rains and water influx. The climate is tropical monsoon, which is dry season, and rainy season. Dry season from December to April, that is risk of salinity intrusion. Rainy season from May to November, risk of flooding, especially August to November from upstream sources. One of the most commonly used methods in resistivity surveys is the Wenner configuration. As shown in the diagram, this setup consists of 4 electrodes, 2 current electrodes labeled C1 and C2, and 2 potential electrodes labeled P1 and P2. These are placed in a straight line and at an equal spacing denoted as A. In this method, electrical current is injected into the ground through the outer electrodes, C1 and C2. At the same time, we measure the voltage difference between the inner electrodes, P1 and P2. Using Ohm's law, we can calculate the apparent resistivity, which is a value that represents the average resistivity of the subsurface materials influencing that measurement. The formula used in Wenner method is ρ is equals to 2 pi AR, wherein ρ is the apparent resistivity, A is the spacing between electrodes, and R is the measured resistance. We can also calculate electrical conductivity, which is simply the inverse of resistivity, and that's given by the equation sigma is equals to 1 over ρ. If the ground is composed of uniform material, the current lines and equipotential lines will remain evenly spaced, as shown in the top model of Figure 3. However, if there are layers with different resistivities, the current flow and potential distribution will change. In the second model, the upper layer has a higher resistivity than the lower layer, so the current bends more deeply. In the third model, the upper layer has lower resistivity and the current tends to spread more near the surface. The weather method helps us understand subsurface conditions by analyzing how electrical current moves through different soil or rock layers. This slide presents the soil sampling and EC analysis method used in the Foddy fields. The researchers used a Wenner electrode setup with stainless steel rods spaced at 5 cm intervals. The electrodes were calibrated in water by dissolving salt and comparing readings with a HANA HI 98331 device. In the field, measurements were taken in two zones. In Zone A, they compared EC at 5, 10, and 30 cm spacing. In Zone B, measurements were made before the summer-autumn and winter-spring sowings, with solids submerged for 3 months before the second round. In total, about 800 EC data points were collected, helping to map salinity levels across different conditions and times. The researchers began by testing in a controlled water environment. The results showed that using the Wenner electrode system at a shallow depth of 2.5 cm gave the best correlation with the HANA HI 98331 device, and in this case, the R-squared value was extremely high, which is R-squared is equals to 0.991 with a root mean square error nearly equal to 0. This suggests excellent agreement between the two methods under ideal homogeneous conditions. However, when it was increased the electrode depth to 2.8 cm, the correlation dropped drastically to R-squared is equals to 0.09984. And this decrease also came with increased salt content, which likely affected measurement accuracy. These results highlight the importance of optimal electrode depth in water EC assessments. This figure shows that soil EC correlation results from HANA device and Wenner method with electrode distance. In Zone A, the researchers measured soil EC at 3 depths, 5 cm, 10 cm, and 30 cm. The researchers collected 100 data points at 5 and 10 cm and 50 at 30 cm. This area was previously flooded by the Mekong River, leaving the soil waterlogged. The device recorded EC values ranging from 0.08 to 0.79, while the Wenner method ranged from 0.1 to 1.2. One limitation the researchers encountered was the device with a length of only 114 mm that couldn't measure at depths beyond 11.4 cm. Therefore, it couldn't provide valid results at 30 cm depth. Despite this, the Wenner configuration at 5 cm spacing produced a strong correlation with the device in the soil environment, with R-squared is equals to 0.7281, which was consistent with our water test. In Zone B, the soil had also been submerged for a prolonged period. Measurements revealed a decrease in EC at 0 to 10 cm depth and a slight reduction in EC at 0 to 30 cm depth. However, the change at 30 cm was not as pronounced. This suggests that long-term submersion reduces EC more at the surface layer than in deeper layers. The researchers then used Kriging interpolation to generate spatial maps of EC at different depths, and these maps clearly showed that EC values were lower at the surface layer, which is 0 to 5 cm. Higher EC values were concentrated at 10 cm and 30 cm depths. As the depth increased, spatial variation in EC became more significant. This reinforces the idea that deeper soil layers retain more salinity or conductance effects, possibly from previous flooding. For the conclusion, Wenner method with DC power, which is effective and affordable for field EC measurement, suitable for use by farmers in developing regions, study limited by small area and lack of historical salinity data, and lab-based EC methods are more accurate but not practical for field-scale use. Wenner method best used to track soil EC variability. And for future research, it should be expand study area, include coastal and flood-prone regions, and also improve EC monitoring strategies in rice cultivation areas. Thank you for listening. And again, I am Manzanal, a third-year geological engineering student of Batangas State University.